Thanks everybody for tuning in. I'm Dr. Aaron Studwell, founder of ExoConsulting. What you're going to watch today is my dissertation presentation from April 8th, 2020, at the University of Houston. The topic was Spatiotemporal Variations in Saturn Zonal Winds based on Cassini's Long-term Multi-Instrument Observations. So I'm going to time tag it to the different tasks. You can break it up, you can watch what you want. Stay tuned till the end, there's a bit of a surprise. And you get to see how everything kind of went. I will say now also, there was a 12-minute gap. That's how big the kerfuffle was trying to get everybody's technology set on Microsoft Teams. So thanks for tuning in. Thanks for staying tuned in. Ask any questions below. If you like this video or anything else on the channel, please like and subscribe below. Thanks a lot. Thanks again. Take care. So now, everybody, thank you for your patience and thank you for being here this morning, and everybody who's been part of this journey, thank you for everything you've done to support me through this. Today's topic are the spatial-temporal variations of Saturn's zonal winds based on Cassini long-term multi-instrument observations, and this is a PhD dissertation defense. Happy 2020. What a crazy year it's been. Oh, it's not giving me the option to advance the page. There we go. Oh boy. Okay. For an overview, we're going to discuss the motivation, the background, the research design, the research tasks. So we're going to break those into 4 tasks. The thermal wind equation, the standard and general forms. Task 2 will be the zonal winds at and above the visible cloud level. So that'll be broken into two subtasks, and we'll get to that in a little bit. Zonal winds below the visible cloud level, the analysis of the Great White Storm of 2010, and then conclusions. And then we'll get to the questions and answers. So when I started at the University of Houston in the Atmospheric Sciences Department, I had given a seminar, and my office mate and friend, Dr. Abigail Corbett, asked me a question during the seminar, or at the end of the seminar: why do we care? And I thought that was a great question, and why do we care? So looking forward, we're going to develop the building blocks to increase our comprehension of the spatial temporal variations of Saturn's atmospheres. So, we can better understand what concepts and physical laws of the universe are. We need to study more than Earth. And I was also asked during this PhD journey, why study Saturn? There's so much to learn here on Earth yet, and there is. But there are things about other planets, and there are things about the gas giants that we can learn and apply back here on Earth. We can validate physical concepts that we develop here on Earth and validate them on other planets. We can show that it's not just a one-off for Earth. And as of last night, there were over 4,100 exoplanets discovered. So as we increase our knowledge of the planets in the solar system, we can increase our understanding of what we're seeing across the light years. So moving forward, when we launch the Webb telescope, we're going to discover more planets. We're going to learn more about each planet. So we take this knowledge we learn in our own backyard, and we can extend it across the light years. And we talked about backgrounds and what are we going to look at, and what data are we looking from. And we're going to start with what the Cassini-Huygens mission was, and that launched in 1997 until the grand finale in September 2017. We're going to have an overview of Saturn, and then we're going to discuss the atmosphere of Saturn and kind of give you a broad brush approach on it, and then we'll really dig down into it as we go along. For the Cassini mission, as I mentioned, it launched in October of 97. It did a Jupiter flyby on December 30th of 2000, and then arrived at Saturn in July of 2004. The original mission was only scheduled to go until 2008, but the mission was extended, funding was extended. When it arrived for the prime mission, it was summer in the southern hemisphere. So as the mission continued and we went to 2010, it became the equinox mission, as Saturn was going through its equinox phase and northern hemisphere was going into spring emerging from the shadows of the rings. Funding was again extended to take the mission into 2017 for the solstice mission, as the northern hemisphere went from spring to summer, and then the grand finale, April 2007 until mid-September 2017 until mid-September 2017. So moving forward onto slide 6, it had 12 instruments, scientific instruments aboard the Cassini. We can see a schematic of it on the right. I'm going to point out the more relevant ones to us, and they're all in this region here. If you can see the mouse cursor, the VIMS, the visible and infrared mapping spectrometer. So we had a visible light telescope and an IR telescope here. The imaging science subsystem, and that consisted of 2 cameras, and we'll get into the details of that when we get to task 2. The NAC, the narrow angle camera, and the WAC, the wide angle camera, and then the SEERS, the composite infrared spectrometer, was down in this region here. And we go back and we talk about the grand finale. Why did we crash it into Saturn rather than just let it stay in orbit until the very, very end? Well, it had used hydrazine as its chemical propellant, which is a toxic substance and can be dangerous in some atmospheres. So the thought process was to not let it crash into a moon or crash through the rings, but rather have a controlled descent into Saturn where it would be destroyed in its atmosphere. We're going to take a closer look at this region here on task 2 as well. Moving on to slide 7. Just a quick overview. The highlights on this slide are the period of orbit being 29.5 Earth years. The time that Cassini was on mission was almost 14 years. So we've captured data from half a Saturnian or Cronian year. So we've actually seen it go through seasonal changes. So having that availability of the data and that extent of data allows us to do a better interpretation and give us a better understanding of these spatial temporal variations. And combined with that, an axial tilt of 27.9 degrees does give it very distinct seasons like we see here on Earth, where Earth we have 23.5 degrees axial tilt and a very rapid period of rotation where it's 10.7 hours, which does impact some calculations. And there's uncertainty about that 10.7 as well as you might have seen in the dissertation. Having an exact knowledge of that actually impacts the zonal wind calculations for the ISS and for the VIMS data. For slide 8, we have that schematic on the right. And what that is on the right axis, we show the atmospheric pressure in bars. And I'm going to distinguish that now in saying that what we're going to deal with in both the dissertation and its presentations in millibars, but this graphic is in bars. The left axis is the altitude with 0 line here being at the bottom edge of the tropopause. We see 3 layers of clouds through this. The water clouds around the 10,000 millibar level, ammonium hydrosulfide clouds about the 2 to 5 bar level, and then the ammonia clouds about the 1 bar level extending up to about between 5 and 700 millibars. That's the tropopause, or troposphere, excuse me. And the pressures there are greater than 100 millibars. For the tropopause, we have a photochemical haze. It's not a very similar structure to Earth. It is a similar structure to Earth. So that across the tropopause, we have steady temperatures, and that is actually the coldest place in this section of the atmosphere. So we have temperatures there of 82 Kelvin. Minus 191 degrees centigrade, and then into the stratosphere we have thinner layers of hydrocarbon haze. The pressures are less than 50 millibars, and again a scenario like an Earth's atmosphere where it does warm up as it reaches towards the ionosphere, and that is because of incoming solar insolation heating those layers. Moving on to slide 9, talk about a flow chart of the research, and we alluded to this earlier. We're going to start with task 1, which are the thermal wind equations, and we're going to discuss the standard and the general forms, And then we'll also have in that discussion why we need a general form, and then in the dissertation itself, we actually showed a validation of the general form. For task 2, as I mentioned, we are splitting that into 2A, which is going to look at the zonal winds at and above the visible cloud layer as measured by the ISS. The data from that will actually help feed into task 2B, which is the zonal winds at and above the visible cloud level with the Sears data. So the data from 2A also feeds into the task 3, which are the zonal winds below the cloud level, visible cloud level, and that uses the VIMS data. And then we have both data from 2A and 2B feed into task 4 on the analysis of the Great White Storm of 2010. Moving on to slide 10, just highlighting that we're going to start task 1. So slide 11. A breakdown of task 1. The thermal wind equation. What is the thermal wind equation? We're going to kind of briefly cover that and why. We're going to look at previous research, and this is going to be these previous researchers are going to be a brief view of it, kind of the more landmark things for brevity's sake. When I first wrote this, we were probably about 67 slides, and as you saw in the emails you received, they're probably down to about 58 slides with some of them transitioned. So for brevity's sake, we'll kind of cut down to the previous research. We'll cover the standard wind equation, the general thermal wind equation, and then we'll hit the conclusions. What is the thermal wind equation? So we're looking at the fundamental principles of the thermal wind equation, in that the atmosphere is in hydrostatic and geostrophic balance. And with hydrostatic balance, what that means is that in the vertical direction, the upward gradient, pressure gradient, is equal to the downward gravity. And geostrophic balance means that on the horizontal, we have a balance between the Coriolis force and the pressure gradient force in the horizontal. So what the thermal wind equation does is it relates to vertical wind shear, which we're going to call VWS through the rest of this presentation, and the geostrophic winds with the horizontal temperature gradients along isobaric surfaces. And an isobaric surface is a surface of constant pressure. So in a barotropic atmosphere, where the density is only related to the pressure, geostrophic wind is there's no vertical wind shear. But when we get to a baroclinic atmosphere, we actually see this vertical wind shear here, with the geostrophic wind at the P0 level being fairly light. But if I go up to P0 minus 2 dP, so whatever we want dP to be, we actually see that higher in the atmosphere when we have a baroclinic atmosphere, which means that density is related to both pressure and temperature. The slopes of these isobaric surfaces are steeper, which means I'm going to have a greater pressure gradient across the horizontal, meaning the geostrophic winds are going to be faster. So I do get a vertical wind shear in here with the baroclinic atmosphere. So we revisit the fundamental principles of the thermal wind equation again, in saying that it goes all the way back to Archimedes. That, when he was in the bathtub allegedly and screamed eureka, and noted that the hydrostatic balance was in force and water, and then that was quantified by Galileo and Lambiancetta in 1644. And I actually did go back and find an English translation of that document and read over it. I do find great interest in the history of the science and history of science. So this has been a very wonderful part of this project, is going back and doing this literature review. For the geostrophic balance, it really kind of first started in 1829 when Gaspard Gustave de Coriolis, who was a mechanical engineer, actually noticed the implications of Coriolis force on centrifugal force. And it was in 1856, so for the atmospheric scientists in the group, William Ferrel, who you will associate with Ferrel cells, first came up with the concept of the centrifugal force being a balance to the pressure gradient force. And in 1938, this was the first definition, derivation, and validation of a standard thermal wind equation by two National Weather Service meteorologists, Vernon and Ashburn, They were working in the Salt Lake City office and noticed, and they're having problems with upper level wind forecasting for the air flights because there didn't. It's still a common problem today, not to this extent. There isn't a lot of sounding data across some regions, so they went through and derived the first standard thermal wind equation, and that was published in 1938. Moving on to slide 14, we can see that the geostrophic wind balance, we're actually going to put some numerics into this. We have the Coriolis force times the zonal wind velocity. In this case, it's just U, which is the east-west component, the zonal winds, and how that is equal to or proportional to the horizontal pressure gradient, in this case the meridional pressure gradient. For the hydrostatic balance, we see the variation in pressure along the r-axis, which is the outward axis on a sphere. So the pointing like out through the top of a parcel, and I'm sitting here using my hands like I'm standing in front of you, offsetting the gravitational force, so rho times g, so the downward force that would be acting on it. So if all four of these are in place and there's no pressure gradient, the parcel is at rest. What will happen here is if there is a pressure gradient, I would get a geostrophic wind. And so this is one of the few forces that does not require a force input to a technical force input to achieve a velocity. So now we're going to differentiate equation 1 with regards to r. We're going to apply the hydrostatic balance, equation 2, and apply the ideal gas law. So this gives us a standard form of the thermal wind equation, where the horizontal wind or vertical wind shear, so the change of the zonal wind velocity as I increase in height along the r-axis, is related to the temperature gradient, horizontal temperature gradient across the meridional direction. Moving to slide 15, why a general thermal wind equation? This was actually pointed out in the 1960s, and then this work has really kind of continued forward ever since then, where it was noted that as we approach the equator and then actually reach the equator, with phi going to 0, the Coriolis parameter then goes to 0, and things just kind of go kablooey from a mathematics standpoint. Add in rapid rotation periods that we see on some of the gas giants and other planets within our solar system, large-scale equatorial jets yielding non-negligible forces in the equatorial regions. What happens is the Rossby number actually increases and doesn't necessarily have to approach 1, but we can get rid of the, when the Rossby number is much, much less than 1, we can start taking into some account some assumptions, and those assumptions go away when the Rossby number starts getting larger. So we can't presume hydrostatic or geostrophic balance. So when we developed the general thermal wind equations, they're found in the momentum equations. So we're going to do the derivation starting in the spherical coordinate system. We'll eventually get it to cylindrical. We're going to look at large-scale zonal flow with the assumption that it's steady and axisymmetric, and that is the case on Saturn. That the U is much greater than V, which is much greater than W. So we're seeing that the zonal is much greater than the meridional, which is much greater than the kind of the vertical velocities. And friction can be neglected. So we don't have, not in the level of the troposphere that we're studying, there is no surface. So unlike Earth, where it's this thinner atmosphere where I do get this boundary layer effects, we can neglect them in the general thermal wind equation, so we don't have to look at friction. So after all the derivation we went through in the dissertation, we wind up with a form like this, where on the left-hand side of the equation, we see the contribution of the centrifugal force and the Coriolis forces along the z. So this gives us our variation in these velocities here with in the z-axis, and then we also look at a case where pressure changes with height, and also that temperature changes meridionally. So we wind up getting a balance of forces here. So we can see that the centrifugal acceleration and the Coriolis force modifies the pressure field because we have this here, but we're going to assume that all this eliminates a meridional pressure gradient. So it has to do that. So there's no meridional pressure gradient here, but it still needs to change. There still needs to be a change in this, or some way to keep it to zero. And what we see is a modification of the effective gravity. And the effective gravity is the vector sum of the gravity and the centrifugal force of a parcel in motion. So how we offset this is we can offset this atmospheric expansion and contraction, which is caused by temperature variations, and that yields the horizontal pressure gradient. So where standard thermal wind equation integrates in the radial direction with a spherical coordinate system, we're actually going to go to a cylindrical coordinate system where the integration path is tangential to the reference pressure. And we'll actually go to a schematic on a couple of slides, or actually this slide, 17, to look at that. So we're going to, by transitioning it to cylindrical coordinates, we still have this del z term on the left-hand side, but the right-hand side is now broken down into here, but by applying scale height through all this, we wind up with the change in pressure along the RC line, which is these lines CD. And I'll change the graphic in the dissertation. I actually added this note after the fact when I was going through the presentation and said, oh, that would really help right there. So I added that. So it's a change of pressure along this line here. And then also the temperature gradient along the z-axis. So the horizontal pressure temperature gradient. The critical latitude 5C1 is here. And this is the location at which the standard thermal wind equation breaks down. That the forces that are captured in here I'll use the term overcome the forces that are represented in the standard form of the thermal wind equation. So we look at this, we say, what conditions do we need of geostrophic and hydrostatic balance? So those are used in the derivation of the standard thermal wind equation, where the general thermal wind equation does not. It does, however, it does present a more exact relationship between the thermal fields and the large-scale dynamics. So on slide 18, we're going to hit the conclusions. We did an overview of the standard thermal wind equation. We provided the derivation of the general thermal wind equation with admittedly simplified momentum equations, but that was through assumptions that we consider to be valid. And we did put an emphasis on the underlying physics. And then on a grander scale, for an application standpoint, and for those, and most of you know me, and I've come from an operational background, to take this to an operational setting for both for gas giants and planetary atmospheres, where the standard thermal wind equation is easier to apply at and just as applicable at the mid and high latitudes, and is actually easy to apply. And the general thermal wind equation is a little harder to apply. It is mathematically intensive, but it is more relevant, applicable in the equatorial zone. So by combining these two forms, we yield a powerful tool in the exploration of planetary atmospheres. Moving on to slide 19, tasks 2A and 2B. So we're going to look at the zonal winds at and above the visible cloud layer with both the ISS and the SEERS data. Going on to slide 20, we're going to take a look at the sensor schematic. We'll go through each sensor, the specifications, how the zonal winds are calculated or estimated. Then we'll look at previous research, and then we'll combine all of that information from the first 3 bullet points. We'll do the analysis results by combining those 2 data sets, and then we'll move on to the conclusions. On slide 21, You see a schematic, so this is a blown up image of what we saw earlier in the presentation. So we see the VIMS IR spectrometer here, the visible cameras here, the electronics back on this side. For the imaging science subsystem, the ISS, we have the NAC and the WAC right here, and the infrared spectrometer, composite infrared spectrometer is right here, and that's the SEERS. So a lot of numbers and a lot of information on one small slide 22. But we're going to kind of cover the highlights real quick. Is where the NAC had a longer focal length and was a narrow angle camera, which gave higher resolution, while the wide angle camera had a 0.2 meter focal length. They both had a lot of filters. The NAC had 24, the WAC had 18. Going back to the focal length real quick, this gave the ability for simultaneous imaging, where the NAC would do the close-up and the WAC would do the wide angle view, which is both used for scientific purposes and also for helping determine the location of the image taken, because the WAC would have the limb in view, so they could do an overlay and get an idea, because they knew exactly how far they were away from the planet. They knew the ephemeral data. So with all that together, they could go ahead and position the image that was taken off the planet. As I mentioned, we had 18 and 24 filters respectively, of which we are interested in 4, 2 methane band, the MT2 and the MT3, which gave 2 very different views of the atmosphere, where the MT3 gave a view of the tropopause in the 50 to 60 millibar range, in the methane band extended all the way down to 1,000 millibars deeper into the troposphere, where the 2 continuum bands, CB2 and CB3, looked into the atmosphere. The lower to middle tropopause, and it's kind of listed as upper tropopause there, 100 millibars for the lower tropopause, and then the upper troposphere, 300 to 500 millibars. Moving on to slide 23, the zonal wind estimation from the ISS data. There are 2 techniques used. The assumption is that the clouds are actually passive tracers of motion. There's an automated procedure which uses algorithms to identify, cloud features over a series of images. So what it'll do is it'll look at the picture, pick out the clouds, and then take 2 images side by side. We know where they were pointing. We know how much time elapsed between the 2 images, so we can determine the longitudinal displacement of the clouds by how many pixels it went and the time elapsed. So this is where it came to be important that you knew how much, what the rotational rate of the planet was, because I needed to know how much the planet moved and how much the cloud itself moved. So by knowing a more accurate version of the rotational rate, we could get a more accurate version of how much it moved, how much displacement was, and therefore you can calculate the wind speed just by taking the distance over time. It became so important that in some regions where we saw easterly winds, they became westerly winds became easterly winds in some locations. And also the automated process is a more efficient and objective process. Looking at the manual process, it's just like the automated process, except it's a manual process. So you're visually looking at 2 images. You're seeing that cloud is that cloud on 2 different pictures. Then you're measuring the pixel distance. What it gave you the ability to do is to eliminate what would be termed spurious matching in some areas where the albedo pattern was more linear, but it was a slower process. So it's done almost as a check in some regions, and it's done out of necessity in some other regions, but it is a slower going process. For slide 24, we're going to look at 2 articles. Porco 2005, or Porco et al. 2005, give everybody credit there. Full publication of the first ISS data analysis. It covered data in 2004, so during final approach, and then it's also on its first set orbit in September. It focused on the southern hemisphere because that's where it was summer and the orbits kind of focused, and they are focusing on taking data down there. So poleward of 15 degrees south. And what it did was confirm or presumed to confirm that the positions of the local zonal max and min were similar in location to the location, to the location and magnitude as was detected by the Hubble and on the Voyager missions. And then we'll go on to Lee 2011, where he and his team looked at data from 2004 and 2009 in the equatorial zone from 20 north to 20 south. They looked at both ISS and Sears data. In the ISS, with the tropopause data, they had noted the winds had accelerated, but deeper into the troposphere, the winds were consistent. And what that was resembling as we were moving from southern hemisphere summer into fall, and the northern hemisphere was moving into spring in 2009, was that in the higher elevations, higher altitudes in the tropopause, that the incoming solar insolation had allowed the winds to accelerate, where deeper into the troposphere they had not received as much insolation yet, and also it's fairly dampened with deeper into the atmosphere, that it doesn't necessarily see wind speed changes over the seasonal transitions, but we're going to show later that they actually do over a longer period of time. And then looking at the Sears data, because this is one composite study, they had noted that the winds accelerated greater than in the tropopause, and that was for the same reason. So that team had noted the quasi-quadrennial oscillation, the QQO, had dampened as it progressed downward. And it did noted that QQO was a stratospheric pattern that was actually in place and was similar to Earth's QBO, the quasi-biennial oscillation. Going on to slide 25, the Sears specifications. With the dual Fourier transform spectrometer in both the mid and far infrared at wavelengths from 17 microns to 1 millimeter, and that was on FP1, and we're going to have a diagram later showing how this all worked vertically through the atmosphere, and then on the mid IR where the wavelength was 7 to 17 microns, and that's FP2 and FP3. And with the mid IR, it actually had increased spatial resolution, where the resolution was 1 to 2 degrees latitude, and that really came down to viewing angle as to what the actual kilometers of resolution was on that point. So continue on the specifications. As we noted, that the radiance data was collected by 3 focal planes, where FP3 and FP4 focused on the tropopause down into the upper portions of the troposphere, and then out into the stratosphere, where FP3 was from the tropopause down to 300 millibars, and FP4 was from 5 millibars out to 0.01. When we look at some data, we'll note that some of the data between 5 and 50, because of that blind spot on the Sears, is going to be interpolated data, and we'll point that out again after. And for the troposphere, FP1 is 300 to 500 millibars. So this radiance data was translated to 4D temperature data from the upper troposphere into the stratosphere, and then the variance of the radiance was with the emission angle, and so you could show it's directly related to the vertical structure of Saturn's atmosphere. So we look at the thermal wind equation that we developed in task 1. We have this 4D temperature field that we're analyzing. So we have this data set sample on the right side of the slide here, where we have this color bar as your legend for temperatures ranging from 80 Kelvin to in excess of 150 Kelvin. On the left side, we have pressure in millibars ranging from 0.001 millibar to 500 millibars, and then we range from really the near polar regions, both northern hemisphere to southern hemisphere. So we could determine through this set of data here, where we know the horizontal temperature gradient along the isobaric surfaces, we could use that to calculate the vertical wind shear. And we use as a boundary condition of the integration the 360 millibar zonal winds that were obtained from the ISS data. Moving on to slide 28. For the Sears previous research, we look at Lee et al. 2008, which looked at data from 04 to 08 in the equatorial region, kind of extending into the mid-latitudes as well. Stratospheric jet, it did determine there was a stratospheric jet 5 to 600 meters per second, outwards or upwards of the 1 millibar level, near 10 degrees south. And this is the strongest atmospheric jet that at that point was discovered in our solar system. And then also Fletcher et al. 2015, February 04 to October 14 is the data it reviewed and really focused on the polar regions. So not necessarily filling this gap here, but it was a different perspective of it, polar to 75 north and 75 south. It determined in the southern hemisphere that the vertical structure, that the maximum vertical wind shear was aligned with the jets, and it was also vertically aligned. But looking at the northern hemisphere, it was a little bit more messy, that the jets were switching between retrograde and prograde, so switching between easterly and westerly, shifting locations, and then the upper level jet was actually south of a deeper jet. So where things were very uniform and structured in the southern hemisphere, northern hemisphere, as it moved into northern hemisphere summer, became a bit more different. Just it changed over time. So it's the spatial temporal variations that we believed existed. We saw in previous research, we kind of worked forward and showed that did exist. So we're looking at different data sets here. We were kind of limited at times by the seasonal structures and seasonal changes, and as to where the data was from. But this first set was from October 04 to October 15, and we're going to look at it in two segments. It is located in the equatorial and mid-latitude region, so 30 north to 20 south. And then we use the MT3 data and the CV3 data from the ISS. So from 04 to 08, we're focused on southern hemisphere data with the MT3, so this is around the tropopause level. We saw approximately 30 meter per second increase between 04. So we're looking at zonal wind speeds here in meters per second on the x-axis. The y-axis is latitude with the equator a little bit off the graph, but we're going from -5 south to -20 south. The solid red line here is the winds that were determined through correlation procedures. And we see the error bars associated with them, and they're very uniform. So that's for 04. We did a tracking wind. So that's the manual procedure here in the red dots as a check. And then 05, we actually applied thermal wind data, and we saw the increase that we see even more sharply in 08. So as we move into, we continue into the southern hemisphere summer, increasing solar radiation insolation, we see the equatorial regions warming, and we see the thermal winds increasing. And then 08, the tracking winds in the blue dots, the correlating winds in the solid blue line, and the thermal winds and the dashed blue line. So we see a solid increase across the southern hemisphere in the winds, between the tropopause winds between 04 and 08. We'll also note that the peak velocity shifted, and this is a typo, I'm just catching now. So we had that the peak velocity shifted equatorward or poleward here between 04 and 08. Moving on to slide 30, we look at the CV3 winds, which are deeper into the troposphere. That there wasn't as many changes between 04 and 08. This is about the 300 to 500 millibar level, and we see some changes, but those changes do kind of occur within the error bar, and they're not as substantial. And part of it is scaling, but really down as we get 15 south, they're almost identical. And we do see this little bit of an increase here around 13 south, but it does come pretty close to where the error bars are. So we're showing that deeper into the troposphere that the tropospheric winds are less susceptible to variations. And then looking from 09 to 15, again, deeper into the troposphere with the CB3 winds, that the increased 50 meters per second in the equatorial region. Again, similar graph structure with the zonal winds on the x-axis. And this is where red is the 2009 data, the green is the 2012 data, and the blue is the 2015 data. We see a 50 meter per second increase in the equatorial zonal winds even deeper into the troposphere as we move into the northern hemisphere, move from spring to summer. The tropical regions are emerging from the ring shadow and receiving more incoming solar radiation. But north of 12, we don't see a substantial difference, and it's within each data set's error bars. Moving on to slide 31, we reviewed the data from 09, so the vernal equinox, to 2015, which is the summer solstice for the northern hemisphere. We looked at the equatorial regions to high latitudes, so we looked from 70 north to 70 south. We looked in stratosphere and troposphere from 0.01 to 750 millibars. As I mentioned earlier, the boundary condition was the 360 millibar winds from the ISS data, and we had mentioned where that data gap from 5 to 50 millibars is on the tropopause. The temperature data was interpolated. So we see a seasonal transition here on slide 32. The graph on the right is similar to one that we saw earlier, where the color contours are temperatures, with the deep, deep blues being around 80 degrees Kelvin and the deep, deep reds being in excess of 150 Kelvin. We see the graph extending from 70 degrees south to 70 degrees north. And what we have here is we're circling an equatorial stratospheric cooling event. But I do want to take a step back real quick and evaluate. And you see in 2009 where they had that very warm temperatures in the stratosphere, even in the high latitudes towards the polar region, and here, and even the warm atmosphere extended in the stratosphere up to about 40 north. As we transition seasons, it did what we'd expect. It did cool across the southern hemisphere and warm rather significantly, rather quickly across the northern hemisphere. As we got into 2015, we see cooling across the southern hemisphere, similar to what we saw here in 09, and then a more uniform pattern north of 30 south, extending into the northern hemisphere. In the troposphere, we saw this really cold pocket here. That did warm as we moved into northern hemisphere summer, with southern hemisphere summer or winter coming into play, and cooler temperatures through the troposphere. The temperature evolution is what would be expected, but what we see in the equatorial region about the 5 millibar height is we saw a warm core of temperatures here. So we saw in excess of 140 Kelvin. By 2012, it's transitioning, and then by 2015, it's cold core with temperatures in this region of around 100 Kelvin. So what did that do to the wind flow? We look at slide 33 and through the application of the general thermal wind, and going to the graph on the right real quick, similar structure to previous graphs, but now the color contours are actually the zonal winds extending from 0 meters per second to in excess of 500 meters per second. And then in 2009, where we had that warm core system around the 5 millibar level, we had zonal winds in excess of 500 meters per second, or approximately 500 meters per second, down to 2015, where they had really almost gone calm. So, and we see on the tropospheric winds, where we had this core here of 450 meters per second and extending up to about the 350 millibar level, they did quiet a little bit down to 375 meters per second, but now they extended upwards to 150 millibars. But the most telling thing here is that zonal wind, the calming of the equatorial jet, which does align with the findings in Lee 2011 in showing that the QQO was in play, where his was published in 2011. We now continued this data and going forward into 2015. So the conclusions on slide 34 for the ISS and Sears data, so visible winds above and at the zonal winds at and above the visible cloud layer. We examined the spatiotemporal variations through most of the Cassini era, from 04 to 15. We did it during the southern hemisphere summer, so from 2004 to 2008. The tropopausic winds, zonal winds, increased, while the tropospheric winds generally remained steady. We did see a more rapid response in higher altitudes due to increasing solar insolation. Then also during the northern hemisphere transition to summer, so 2009 to 2015, we saw deeper tropospheric zonal winds, increase in the equatorial regions, and steady polar to 12. And again, that was associated with increase in solar insolation as the rings moved out of the shadow, or the area moved out of the shadow of the rings. And then also the stratospheric winds, consistent with the Saturn equatorial oscillation and the QQO, it decreased in the equatorial region from about 500 meters per second to 0 as it transitioned into summer. Moving on to task 3, this was research that was originally published in 2018 in Geophysical Research Letters. Saturn's global zonal winds is explored by Cassini VIMS 5-micron images, and that is really what task 3 is all about. So we mentioned earlier, and we've kind of looked at all the sensors coming up into the VIMS. So this graph or image again on the right is the atmospheric pressure on the right-hand axis. Left-hand axis is altitude in kilometers from the tropopause. But now we actually see where are the sensors looking. And so the VIMS is actually, what the VIMS actually does, and we'll cover this in a minute, it actually detects the outgoing solar or the outgoing infrared radiation that we believe is emitted from around the 5,000 millibar level, I was going to say 5 bar level, and backlights the clouds at this level here, the ammonium hydrosulfide clouds. So they actually wind up seeing a negative image. It'll see the white outgoing radiation in the black clouds, and we actually reverse that at times when we want to do actual visualization of it. So the VIMS looks at this level. For the Sears focal plane 1 is this part of the troposphere into the tropopause. Up here, FP3 is across portions of the tropopause down to the troposphere, and then outward through the stratosphere for FP4. And then the ISS sensors look in this region here. So down into the troposphere and then across portions of the tropopause and into the upper troposphere. We're going to look at the specification for the VIMS, which is back down in here again. We're going to look at how the zonal wind estimations are calculated, which will seem very similar to the ISS. So we're going to kind of skim over that. Again, we'll look at previous research, and for brevity's sake, we've kept that to one slide. Analysis, results, and conclusions. The VIMS was a hybrid instrument, so we had the visible and the near-infrared spectrometers on it. 64 by 64 pixel spectrograph. While it observed from the 0.3 to the 5 micron range, we were really focused on the 5 micron band, which was about 4.6 to 5.1 microns. Again, as we mentioned that is estimated to emit from the 5,000 millibar level. It directly observes the thermal emissions, and so the clouds are backlit against those IR emissions. So we're looking at the troposphere at the 1,000 to 3,000 millibar level. Clouds and tracking analysis, automated and manual, so that is identical to what we did with the ISS data. Again, and then the backlit clouds, they are just very discrete in nature, so they're easily differentiated for the wind speed calculations. You can identify the backlit clouds in day and night because we're looking in the infrared. And the clouds at this level actually persist for many days, so we can get several sets of zonal wind measurements can be carried out on this. For the previous research, we went and looked at two articles, pulled two articles from Baines et al., one from 2005, where this was the first publication of VIMS data. They looked at just October of 2004, and then they looked in the equatorial zone of the southern hemisphere. The tropospheric winds were approximately 350 plus or minus meters per second within the equatorial jet. However, it was noted that it was inconsistent with research from the Voyager missions and also from Hubble. Their belief was that this instrument was looking at different levels than the Voyager was, but it was also possible that over time, from 2004 to when Voyager had passed in, the Voyager missions were 1980 and 1981, and then the Hubble data was from 94, that over that 10 to 20 year time period that the wind speeds had actually changed. And then Baines 09 had looked at June of 2008 in the polar region, and that is that animated GIF you see on the right hand side, and I hope it is not causing anybody any lag. We looked at the northern, as I said, the polar region, and then we actually looked at the winds, or they looked at the winds in the hexagonal storm. They have noted that the hexagonal storm, that the axial hexagon itself remains stationary, but a westward propagating Rossby wave was in it with a wave speed of approximately 125 meters per second. In this storm, or in this hexagon, there is minimal vertical wind shear downward through the storm. Going on to slide 40, look at our results. On the right-hand side, we see a familiar looking plot with zonal winds on the x-axis. Negative values represent easterly flow, flow from the east to west, so easterly flow, while westerly flow is represented as the positive value. And then this is the first graph to be made pole to pole with long-term data with both the VIMS and the ISS. And this shows the VIMS data from 2015 and 2016, while the ISS data is from 2004 to 2008. So this shows the actual first millibar, a global profile at the VIMS level. We do detect two areas of vertical wind shear. First, the equatorial region, it is stronger in the deeper troposphere at the 2,000 millibar level. And then in the mid-latitudes, we see where the mid-latitude jets are stronger at the 300 to 500 millibar level. Slide 41, if you go through the paper or the dissertation, you'll see a lot of the mathematics and the thought process behind this. Again, with the thought process now that we're at slide 41 in about 3/4 of the way through it, we're going to just show this like this. We do see on this right-hand graph two sets of dashed lines near the minima of the, or the, you can call it also actually the easterly, in some places the easterly max of the jet flow. And when these lines represent positive curvature, so the second derivative along these points are if we have the jet flow is within that those dashed lines, what we have is positive curvature of the second derivative of the zonal component of the wind is greater than 0. So that is associated with the fact that we have barotropic instability with a positive curvature. This barotropic instability can yield waves and turbulence. And we're also showing that a few easterly jets are unstable, particularly at in the polar region at 79 north and 77 south. The remainder are marginally unstable. The implication on this is that the zonal winds are baroclinic. And what do we take from that? That we also look at regions where we look at the static stability, and we'll kind of talk about the convective instability in a second. With it, the static stability of n squared greater than 0, which it is in almost every single region here, except maybe right at the jets, and we could zoom in on that at some point. And this is this is over a period of time. So the n squared is here along the x-axis, and then we have the latitude along the y-axis, and then on this one we have n squared. It shows that with n squared greater than 0 that it is convectively stable, and we have these high values in the southern hemisphere where it's still summer in 08. With the increased solar irradiance at upper altitudes in the upper atmosphere, it winds up really making it convectively stable, because with the warm air over the cooler temperatures, you're not going to get any lift, and it's going to yield a higher static stability value. We do see convective instability. It points here on this third one over when Ri is greater, the Richardson number is less than 1. We see some values of that in the equatorial region. And then when it's also, the Richardson number is less than 0.25, which we see right in the polar regions, right in the North Pole, turbulence can be sustained. For the VIMS results, focusing on the polar region now, polar to 60, and this is both for the northern and southern hemisphere. So this graph, and this is on slide 43. So for the North Pole, we're here, 60 north to the North Pole. We've looked at data from 08 through 2016, 2017. We can see equatorward of around 83. We see that the temperatures, or the zonal winds, actually really remained the same. And we see those lines nearly overlap in places. The biggest difference outside of the measurement error is in the polar regions, in this northern polar jet, which we see right here on the right in that annular region around the North Pole. In that tight little region right there, we saw winds weaken as we went from northern hemisphere winter into the summer months. We did not see such an occurrence at the South Pole because it was really going from fall to winter in the South Polar region. So from 06 to 16, we saw a little bit of a weakening from around 170 to 150, but you do see some measurement error bars coming all the way out to 170, so this is not with a high amount of confidence. So as it do note marginal changes within the error bars. Going to the VIMS conclusions for task 3 on slide 44, we put together the first global comparison of ISS and VIMS data. We had a general consistency of wind structures on a planetary scale, with the exception in the equatorial region, along with mid-latitude jets. We looked at easterly zonal jets being as barotropically unstable, and some can have a conditions of being baroclinically instable. Polar VIMS zonal data from 60 degrees north to the pole and 60 degrees south to the pole, they were generally consistent from 06 to 17. The one exception was the weakening of the northern hemisphere polar jet around poleward of 84 north. We're going to finish off with task 4, an analysis of Saturn's Great White Storm. Going on to slide 46, these topics are going to be an overview of the Great White Storm, previous research, analysis, and looking at asymmetric expansion, and the conclusions. Slide 47, these Great White Storms are the largest convective cumulus storms that we've noted in the solar system. They do occur infrequently, typically every 30 years, with the first one being noted in 1876. The 2010 Great White Storm was, one could say, 10 years early. It was an outlier because it had only been 20 years since the previous storm in 1990. However, we are very fortunate that it was early. Saturn was showing off a little bit because Cassini was on station then. We were fortunate that the prime mission was extended, and we were also fortunate that it didn't wait until 2020. Well, that would have been an event. Add that and everything going on, and we would have had Cassini not on station. It generally develops, or has always developed, from a single outburst point and expands zonally. It has only occurred in the northern hemisphere to a larger extent. Smaller synoptic scale storms have been noted in the southern hemisphere, but when these great white storms have only been noted in the northern, alternating between the equatorial zone and mid-latitudes. Generally, they'll persist from 25 to 55 days. Again, this was a case of Saturn not being shy. It lasted about 195 days. It formed on December 5th, 2010. It continued through approximately the 12th of 2011. Cassini was not pointing at it every single day, and when Cassini went back and pointed at it, it was gone. At its max, the zonal length was on the order of 280,000 kilometers, so it encircled the entire planet. Meridionally, from top to bottom, at its max, it extended over about 21,000 kilometers. It developed in Storm Alley near 35 North. So this region storm development is also co-located with the westerly jet. It was convective. There was lightning detected. And it did have asymmetric expansion, which is the point of this research during the zonal growth of the bright clouds. So as it grew out of the outburst point, it expanded towards the equator, but poleward growth was limited. So by the time the bright clouds had circumnavigated Saturn, the top edge of the anvil had moved across the bottom edge, or the southern part of the storm's head. So it had really kind of formed and pushed downwards. Previous research, Sanchez La Vega had looked at the 1990 storm. This was a very detailed account of it. He went through and looked at the 5 phases, which were defined, and then he really kind of into 4 phases, or he looked at the 5 previous storms and just moved it into 4 phases. Even the 1876 storm was very well documented with pictures, and impressively, they are still available. And Fisher 2011, Sanchez La Vega 2011, they actually both published in the same magazine, the same issue. Sanchez La Vega was 7 pages, and it was ahead of Fisher. Each article was 7 pages long. So that was the first published articles about this storm. Between the two of them, they examined the drift and the growth rate. They examined the CAPE, which is the convectively available potential energy, and estimated it to be over 11,000 joules per kilogram. And a vigorous storm on Earth, by comparison, will have between 4,000 and 5,000 joules per kilogram of CAPE, an updraft speed of 150 meters per second approximately. And the bright clouds ranged from approximately the 150 millibar to 400 millibar level. Hovenmuller diagram here from December 2010. Its outburst point through August 2011. So even in March, it was still visible at the outburst point. You could see where the tail had gone, wrapped around at west longitude 0. So you could call it akin to the Greenwich mean line. Around here, you see where the tail continued across the date line and then moved south of the head, cutting off here. The northern edge of the head was cut off at that blue line here, approximately 42 north, and extended down to the red line down here with an unfortunate typo here. This should be 21 north here. The black line marks the center latitude at 34 of the storm's head. The asymmetric growth has been shown. Well, the zonal mean, or the meridional gradient of the zonal mean of the quasi-geostrophic potential vorticity, henceforth known as QY bar, the horizontal mixing actually limited by the meridional gradient of all that. So that's been noted on Earth's stratosphere And so we took this approach and looking as those large magnitudes can act as a transport barrier. So the QY bar consists of three terms: the data term, which is a meridional gradient of planetary vorticity, the negative or subtract the U bar YY, so it's the meridional gradient of the relative vorticity. So that actually winds up going back and looking at zonal wind speed, and then a stretching term, which is primarily determined by the vertical wind shear, which is set here as the zonal wind mean out through the vertical on the z-axis, and we have some stability parameters in here as well as Coriolis effects. So the two vorticity-based terms are straightforward, but a little bit of things need to be looked at with these. Saturn's oblateness requires consideration of the effective radius because the radius varies with latitude. The second term assumes that the zonal wind is dominant, and relative vorticity winds up being the meridional derivative of zonal winds. That is very, very, it's straightforward. That winds up being a much more straightforward term than the first term. The stretching term is not as straightforward. We actually have to go to a log pressure system, and then we combine the use of the CB2 data along with the Sears data to calculate the vertical wind shear du bar dz, which was in the third term of this equation and related to the general thermal wind equation. So we go back to that flow chart and we can see where the ISS and the Sears data now comes into the play in this analysis. Moving on to slide 53, the right side on the graph, the vorticity gradient is shown across the x-axis. Across the y-axis, we have latitude in degrees, and we go from 10 degrees north to 60 degrees north. We have marked off here the southern edge of the storm, the head of the storm, and the northern edge of the storm. We have the terms, the contributory terms here, the beta term, the U negative UYY term here in blue. The beta term is in red. The stretching term is in green. The sum of all these terms is the solid darker black line here. So the stretching term is really the meridional temperature gradient, which is related to the thermal wind equation, and then also the buoyancy frequency. And we examined 3 layers within the bright cloud base on the Sears data. So we're going to show this graph again, and we're going to really focus on what this graph is showing. It combines all 3 factors into the QY bar. The northern hemisphere minima at around 20.5 north is shown here, and that's also the so the minima in the QY bar term is here. The maxima is approximately 41.5 north, so almost directly aligned with the northern edge of the storm. We look at that northern maxima and the contributor here. The primary contributor here is the easterly jet, so we have a sharp and distinct change in vorticity here. We also have the vorticity jet, the stretching term here being an increasing contributor as we approach that northern boundary. Far and away at the southern edge, at the minima, we see the stretching term contribute where there's a strong vertical variation in the zonal winds. Moving on to slide 55, the conclusions on the Great White Storm of 2010. We had calculated the QY bar across the across the northern hemisphere during the time period of the 2010 Great White Storm. We showed that QY bar minima and maxima acted as boundaries to meridional mixing, yielding the Great White Storm's asymmetric growth, and that QY bar may play an important role in the maturation of gas giant storms, both on the synoptic and the planetary scale. Moving on to slide 56, overall conclusions. Going back to task 1, the thermal wind equation. We developed a general form of the thermal wind equation that does not rely on the approximations of hydrostatic and geostrophic balance. We offer a connection in constraints of thermal and dynamical fields along this cylindrical direction, and we provided an increased accuracy in the equatorial zone. We also were able to discuss that the standard and general forms of the thermal wind equation can be paired for global analysis. For task 2, we looked at zonal winds at and above the visible cloud layer. In the first part, we looked at changes during the southern hemisphere summer, where the tropopausic winds increased while the deeper troposphere winds were steady, which implied a more robust response in these upper altitudes to the incoming solar radiation. We also looked at the northern hemisphere's transition from 09 to 15. The deep tropospheric winds increased in the equatorial regions. It was steady north of 12 north, and increased in the equatorial regions as it emerged from the shadows of the rings. We also looked at the stratospheric zonal winds. They decreased in the equatorial regions during this time period from 09 to 15 from 500 meters per second to 0, reinforcing or aligning with the QQO and the SBO or SEO, apologies. Task 3, the zonal winds below the visible cloud line. First global comparison of the ISS and the VIMS data. It was the first imaging of the VIMS data on a global basis from pole to pole. We showed the general constancy of the wind structure on a planetary basis. However, we did highlight changes in the equatorial and mid-latitude regions. We discussed that the equatorial zonal jets were barotropically unstable, and some even may be baroclinically unstable, which would relate to turbulence. Polar VIM winds, poleward of 70, were generally consistent from 06 to 17. A small jet in the annular region of the hexagonal storm was the exception as it decelerated over time around 87 north. And then finally, we looked at the asymmetric expansion of the 2010 Great White Storm, that the QY bar maxima and minima acted as boundaries to the meridional mixing and yielded an asymmetric growth, and furthered the implication that the QY bar may play an important role in gas giant storms, both on a planetary and synoptic level. And I know we're going to go to Q&A, and I know we're going to have a discussion here. But for now, I would really like to thank everybody for attending, viewing, staying through the early problems, and your patience with all this, and your help and support during my dissertation work. Three, two, one. Thank you for tuning in today. I'm Dr. Aaron Studwell. I'd like to thank everybody for, I just said thanks, so thanks. Actually, I'll just let it go roll from here, and then we'll go 3, 2, 1. Thanks everybody for tuning in. I am Dr. Aaron Studwell, founder of ExoConsulting, and what you're going to watch today is my dissertation. I presented it on April 8th, 2020. So this crazy year we've had. So exactly 6 years ago, well, that actually worked. And I can go from here and go 3, 2, 1. Thanks everybody for tuning in. I'm Dr. Aaron Studwell, founder of ExoConsulting. And what you're about to watch is my dissertation. Okay. 3, 2, 1. Thanks everybody for tuning in. I'm Dr. Aaron Studwell, founder of ExoConsulting. What we're going to watch today, or what you're going to watch today, is I'm not scratching my face. I'm not scratching my face. I'm just not scratching my face. So, okay. 3, 2, 1. Well, I needed more stuff for bloopers. 3, 2, 1. Thanks everybody for tuning in. I'm Dr. Aaron Studwell, founder of ExoConsulting. What you're going to watch today is my dissertation presentation. I should not fuffle in saying that. Okay, 3, 2, 1. Thanks everybody for, no,
No. 3, 2, 1. Thanks everybody for tuning in. What you're going to watch today, and I want to introduce myself first. Okay. Really, I'm got this. This is like take 8. Okay.